So, good morning once again. Today we are going to discuss the alpha emission. Alpha emission, or the formation of a particle, or formation of a particle in a box. Particle in a box, or we can say that is a square well potential, or we can also say it as a Coulombic potential. In a periodic lattice. In a periodic lattice. Actually, we know that by considering a lattice system or lattice point, the atoms are periodically arranged in this. I consider these are the lattice planes, and in these lattice planes, the atoms are periodically arranged. Here is one atom, here is another atom, here is another atom. Then, based on the nuclear physics, here we want to go to discuss about alpha particles. So we can consider as alpha is a helium nucleus. So helium 2-4. Atomic number is 2, mass number is 4. So the helium nucleus, or within the helium nucleus, there is nuclear force is present. That means nuclear force of attraction that opposes the Coulombic repulsion of the positive charges within the nucleus. Because protons and neutrons are present in the nucleus. So within the nucleus, there has only positive charge, which are by the electrostatic, which are repulsive. But a very strong force in a very short range, because the size of the nucleus is approximately 10 raised to minus 15. So very short range, very strong force. A nuclear force is formed, and this nuclear force combined this all nucleons or this all protons within the nucleus. If consider Z number of proton is there, then Z number of electron is also present in the outer orbits. So if Z is the number of proton, the total charge is equal to Z into charge of the one electron, or E plus, that we can write it as. So by considering this nucleus, within the nucleus, there is a strong attractive force is there. And when we comes from the center to this region, or at just radius of this nucleus, or let this is a point R1. R1 is the radius of the nuclear alpha particle. And consider this is the alpha particle, or helium 2-4. And R1 is the radius of the nuclear alpha particle. Attraction, here is the attraction is approximately equal to the nuclear radiation. So up to here, up to the nuclear radiation, there is attractive force. That means these protons are combined together within the nucleus up to the radius of this nucleus. So this is in the case of a one atom. Here nucleus around electron is present. Here nucleus around present is, and electrons is present. So let me consider this is a positive charge, and when we go from here to here and here to here, there are large number of electrons are present in the orbit. So maximum repulsion is present at this center. Very, very important. At the point between these two lattice points, here we get the maximum point. That means here we obtain a potential well like this. Here the repulsive force is minimum. So in the case of a periodic lattice, the potential is maximum at the midpoint between two nucleus. So R equal to R1 എന്ന് പറയുന്ന ഒരു പോയിന്റ് എടുത്താൽ R1 വരെയും ഒരു റേഡിയസ് ഉണ്ട്. അതിനുശേഷം കൂളോംബിക് റിപ്പൾഷൻ സ്റ്റാർട്ട് ചെയ്യും. ബിക്കോസ് പുറത്തോട്ടുള്ള ഓർബിറ്റുകളിൽ ഇലക്ട്രോൺ മാത്രമേ ഉള്ളൂ. ഇതിനും ഒരേ ചാർജുള്ള നെഗറ്റീവ് ഇലക്ട്രോൺ, ഇതിനും അതെ. സോ ഇറ്റ്സ് ആർ റിപ്പൾസ് ടു ഈച്ച് അതർ. So actually here we can say it as there is a periodic potential is formed. And this periodic potential in a periodic lattice, that is referred as the Bloch potential. So for this considering, we are alpha particle emission, alpha particle nucleus, and we can say these points. There is a how it is formed. In the case of nucleus, there is only the attractive force or strong nuclear force is there. And after that, the Coulombic potential is start. And we can say it as in a periodic lattice, it is called Bloch potential. Bloch potential in a periodic lattice. Now, this amount of this Coulomb potential, Coulombic potential, we know that it is directly proportional to 1 by R. By Coulomb's law, 1 by R square force of F. Then there is electrostatic potential is there 1 by 4 pi epsilon 0 Q by R. It is inversely proportional to R. Here the value is equal to 2 into ZQ1 Q2 by R. This is the total Coulombic potential developed outside of this nucleus, outside of this alpha particle. So by considering a graph, we can draw it as in terms of distance from the center of the nucleus versus the potential. Let's consider here, this is the potential in the y-axis V of R with respect to R, the position from the center of the nucleus. So that this is the point 0 or origin. So we can consider a maximum limit. Here we want to consider a limit and consider this is a region. That is the total energy of our alpha particle or the total potential. The particle energy of this alpha particle or the alpha particle energy. And consider this is the value of alpha particle energy. And also up to a particular point R1, the nuclear attraction is there. So let's consider nuclear attraction in the y-axis. And the amount of Coulombic repulsion in the positive y-axis. So it has a particular value. If Coulombic repulsion, this is attraction. So one if it is draw in positive side, another we can draw it is in negative side. So let's consider the graph is starting from here. At a particular nuclear attractive force is there up to a point R1. And this graph is coming to, and it is sharply decreased or exponentially it again decreases. When R increases, Coulombic repulsion decreases. Let's consider the two atoms are very close to each other, the repulsion is high. If two atoms are very large distance separately, the number of electrons are very, so compared to this point, this is the point of separation, so potential is reduces when the distance is increased from the center of the nucleus. So this is the nature of the graph. And by considering here, we can consider the Coulombic potential from this point to this point. So here let's consider this is a point that we can call it as R1. And here this is a point we can call it as the point R2. So up to R1, there is nuclear attraction. Beyond R1, it starts to Coulombic repulsion, and the maximum limit is up to R2. That means, let's consider the R is a point between this one. So R1 greater than R greater than R2. That is our potential well, or this is our Coulombic. The Coulombic potential due to a periodic lattice. So for more simplicity, we can say it as, here we obtain a one-dimensional square barrier or barrier. This is the boundary condition. We also know that at R1 and at R2, we obtain two boundaries. So, and within this region, it acts as a Coulombic potential region or one-dimensional square well or square barrier within R1 and R2. So R1 is the point up to nuclear attraction is there. Beyond that, Coulombic repulsion is started, and there is a particular limit or maximum limit. And beyond that, it is started to decrease exponentially. And actually, from this, we can write it as a transmission coefficient. That is, the ratio of this exponential decrease, the transmission coefficient T equal to this exponential decrease. That means exponential of minus of square root of 8m by h square into V0 minus T into small m. Here we can say it as, if A is this barrier limit or this width of our barrier, the potential is greater than to the energy. So let's consider this is a point V, the potential is maximal limit. Then the transmission coefficient due to this nuclear attraction and Coulombic repulsion, the transmission coefficient T is equal to or approximately equal to exponential minus decay of this 8m by h square, where m is the mass of our alpha particle. If we are considering the alpha particle, that is the mass of our alpha particle. Actually, theoretically, we can say like this. But actually, there is a law, Geiger Nuttall law, in nuclear physics. Geiger. Geiger. Nuttall. Actually, this is a law in nuclear physics that is connecting the disintegration and this transmission coefficient. And in quantum mechanically, by considering this law also we can say or interpret in terms of quantum mechanically by expressing the theory of this alpha emission. So theoretically it is valid, and experimentally it's not be a perfect square. ഒരു പെർഫെക്റ്റ് സ്ക്വയർ ആയിരിക്കില്ല, അല്ലെങ്കിൽ സ്ക്വയർ വെൽ ആയിരിക്കില്ല. And within this region, the alpha particle has very high velocity of the order of 10 raised to 7 meter per second. So we can say that the alpha particle is moving, it start to collide here and also collide this barrier, and approximately 10 raised to 21 times it collide in a second in this barrier. So this much of limit we can say it as, it can be considered it as a square wave. Large number is collision is there, cannot be take the prediction, because there is a actually we know that if we find out the position, we can find out the time, or the uncertainty is there. So we can be expressed it as a perfect square wave. Square wave potential is developed between or within a periodic lattice. That also the law is valid, the laws of or it also it can be explained. The square wave potential also in terms of nuclear law or Geiger Nuttall law. So this transmission coefficient, T is a transmission coefficient, we can find out the number of probability. Actually, I already say that the probability is very high and it is approximately is equal to 10 raised to 21 times. So we can write it as the probability density P equal to 10 raised to 21 times the total times of this transmission coefficient. Our transmission coefficient means a number of transmission. Here sometimes it is transmitted if energy is greater than, otherwise it collide this wall into to go into the direction or the backward direction. So by obtain the probability, the reciprocal of the probability is gives the mean lifetime. Actually, in nuclear physics, we know that the average lifetime of a nucleus, that is a mean lifetime. And also we studied the half-life. So the mean lifetime tau is equal to 1 by P is equal to 1 by 10 raised to 21 times of transmission coefficient, or 10 raised to minus 21 times of total transmissions. Now, if tau is here, in terms of tau, actually in terms of this 1 by P probability or tau, the Geiger Nuttall law says that, let's consider lambda is equal, or natural logarithm of lambda is equal to a plus b into a is a constant, b is a constant, lambda is a disintegration constant. എനിക്ക് തോന്നുന്നു നമുക്ക് പ്ലസ് ടുവിൽ പഠിച്ച n is equal to n0 e raised to minus lambda t. Exponential decreases the number of disintegration and the time increases. ഹാഫ് ലൈഫ് ആകുമ്പോൾ ന്യൂക്ലിയസ് എത്രയുണ്ടോ അതിന്റെ പകുതിയാകും. അപ്പോൾ അവിടെ നമ്മൾ പറയുന്നത് ടി ഹാഫ് is equal to 0.693 by lambda. And lambda also the disintegration constant. And the reciprocal of lambda is the mean lifetime. Here also, we can consider this tau is equal to 1 by P. And this logarithm of lambda is equal to a plus b into e. That is the Geiger Nuttall law. And in this case, by considering quantum mechanically the decay constant lambda, this decay constant lambda is equal to 1 by tau, that's equal to 10 raised to 21 some time of our exponential decay minus 8m by h square into v0 minus e a square all raised to 1 by 2. This is for only for up to this. All square 4 all raised to 1 by 2 4 up to this 10. So this is the value of this disintegration constant in quantum mechanics. So in quantum mechanics, in a periodic lattice, the logarithm of this lambda is equal to a plus b into e. and it also satisfies the Geiger Nuttall law. And this case, in the case of a periodic potential lattice, and in a periodic potential, the nucleus where the potential is minimum, and the point between two lattice point at the center of the point between two lattice point, or the center of between two nucleus at the potential is maximum. So the periodic potential is developed within a crystal lattice itself, and it's obey the Geiger Nuttall law, and we can predict or express it is by in terms of this alpha particle emission. Thank you.